Welcome back. Now, we are going to look at the two other processes which are the important thermodynamic processes. As you recall, there are four processes that we are looking at here. One is isothermal that we already looked at, which is with temperature being constant, and you saw that isothermal process leads to certain calculation of the first law of thermodynamics. And then the second one was isochoric, where we looked at the constant volume, and in that you also looked at that we are essentially supplying heat to the constant volume container, and that is when we also use the first law of thermodynamics to calculate the internal energy. And so, now we come to the part that with the understanding of running virtual molecular dynamics simulation, understanding that part. Now, we go to two other processes. One is called isobaric. What we mean by isobaric is we are keeping the pressure constant. So, if you look at your slide now, you will look at this PV diagram, and in that pressure versus volume diagram, what you are looking at here is you are looking at the process that has pressure point 1 and 2. So, the pressure is kept constant, that means we have the constant pressure, however, the volume is changing. So, what we are doing at the same time we are keeping the temperature constant from the point 1 and 2. So, what we are looking here is between the two isotherm we start with certain temperature T1 at equilibrium, then we provide some more pressure. When we provide, the volume of the gas changes, and if you look at that time the temperature of the gas changes as well to T2. But we are at that isotherm number 2, which is T2 isotherm, and if you look at work done on the gas is the negative of the area under the PV curve. So, this is a situation where it becomes isothermal situation. So, it's isotherms are the initial and the end point, but in between there is change of pressure, and that pressure is kept constant while the volume is changing. So, if you look at we are going from temperature 1 to temperature 2 with the expansion of the gas. So, volume is changing from V1 to V2. When the gas expands from V1 to V2, the pressure is kept constant. So, that is why it is called isobaric process. So, if you look at then the work done by the gas is pressure, which is a constant, multiplied by delta V, which is a change in the volume. And if you then look at, because we went from isotherm 1 T1 to T2 temperature, we have also supplied it certain heat. So, now if you look at the total energy that is given to the system, it has both heat and the work under constant pressure, and the work is done by the expansion or contraction of the gas. So, if you look at, that is where we are able to now look at the isobaric process, where the internal energy now is equivalent to both the work as well as the heat supplied to the system, and we will calculate that as we move forward. But going back to the diagram on your slide, you can see here is the area under the curve for the PdV curve, which is between V1 and V2 volumes and the pressure being P, and the pressure is kept constant when the volume is going from V1 to V2. That area is the work, and T1 to T2 when the temperature is moved, we have also supplied heat, and that is where therefore, it takes more heat to effect given temperature change, and that is isobaric process. So, molecules rebound with the same speed and gas internal energy does not change. So, if you look at, this is the stationary piston. If you look at the slide here, now we are looking at the situation that we are moving the piston, and what it is happening here is it is keeping the pressure constant because of the movement of the piston while the volume is changing. So, rebounding of the molecules have lower speed as energy is transferred to the outer moving piston. With the decrease in internal energy comes up a drop in the temperature. So, we are looking at, again going back to our diagram, we are going from smaller volume to higher volume. So, there is an expansion in this case. Now, we go to the next slide, and if you look at here the piston at initial location, it has smaller volume. When you go to the next one, now it has larger volume, but it is moving at a speed. So, that we are essentially reducing the temperature, and that goes back to the Charles law, where we knew that as the volume increases, the temperature goes down, or if you increase the temperature of the gas, then the volume will grow. So, now with that understanding, we are now able to understand how this thermodynamic equation will work. So, let me give you a little bit of what we have done so far on your equations, and those equations you can see on my document camera. So, let me bring that up. Let us see, where is the document camera? There it is. So, now what we are going to do, make it full screen, that is good. So, the reason I want to go through some of these equations, because I want you to understand the process that is happening around this. So, we are going to start with the equation of first law of thermodynamics, which says very clearly that there are two things which we are supplying to a system, and let us look at a system which is cylinder with a piston. So, this is our thermodynamic system, it is at the stage 1. Okay. Right. So, now what we are going to do is write the equation which is Q plus W is equal to delta U, and we understand this is the heat supplied, and this is the work, and this is internal energy. All right, you have that. So, now if you look at in the first case, where what we said is going to be isothermal. So, what we are doing, we are essentially keeping the temperature constant, and we are going to change the this is P1 V1. We go to another situation which is P2 V2. So, this could be a compression cycle, and in that case, because we are not supplying any heat to this system and temperature is kept constant with a heat bath, let us say there is a heat bath, there is another heat bath, and the temperature is T1 and it is also T1 here, then the what we look at, the work done is equal to integral of from V1 to V2 P dV. So, we got that, and we have to put a negative sign, because if you look at here, because we have not supplied any heat for this equation, Q becomes 0. So, if you look at this simple algebraic equation, delta U becomes minus W, and that is where we are looking at this equation that is consistent with that. Now, let us say if we take the same system here with the piston, but we are now going to put a flame below that. So, here is the flame, and then we are heating the system, supplying heat to it. So, in that case, if you look at this equation which is we are looking at the delta U. So, we are only providing the heat. So, in this case W, the work becomes 0. So, Q becomes N number of moles multiplied by CV, which is your specific heat multiplied by change in temperature delta T. So, now let us look at the isobaric situation, which is an important situation, and that will also lead us to connect between the two specific heats. So, now let us look at that situation. So, in the isobaric situation, so if you look at this system, we are supplying heat, at the same time we are allowing this piston to move. So, there is a P dV happening, delta V happening here, there is also delta T happening here. So, there is a compression cycle as we looked at here, these isotherms, this constant pressure, and then this goes from V1 to V2 expansion, this is expansion cycle. So, now what we are going to do for isobaric situation, we have Q has two components, we are providing both heat as well as work. So, in that case we are looking at N C P dt, because this is at constant pressure, and also we are looking at the heat that is supplied with the work is N C V dt, where the volume is being kept constant. So, if you look at the Q becomes N C V dt, when the volume was constant and we are giving the heat, plus P dV, which is then the change in the volume. So, if I now look at the Q supplied, which is equal to N Cp dt at constant pressure. So, now we have equation where N Cp delta T is equal to N Cv delta T is plus P delta V, and now you know this PV is equal to nRT. So, now that becomes, we are going to now divide this whole equation by some of the quantities. So, what we are left with Cp is equal to Cv plus R, and that becomes the relationship between the two specific heats and the R, which is universal gas constant. And that is coming from ideal gas law, which says PV is equal to nRT. So, this gives you a now good idea that in isobaric process we have both specific heat with the constant pressure and specific heat with constant volume, and that is where these equations become important for us to understand that how they connect are connected by something that we call as the ideal gas law. So, this is an important development that we did with isobaric situation, and so Cp is equal to Cv plus R, and with that now we are able to deal with what kind of situation we can create with an isentropic system, where we are going to look at the ratio of Cp over Cv, and that will be a factor called gamma factor, and we will vary the gamma factor for an isentropic process, and now you will be able to understand the diatomic gases versus monoatomic gases and how does that gamma factor changes with the molecular structure of the gases. Thank you.